Okay, picking up where we left off, I said we were going to find the wavelength of electromagnetic radiation given off by an actual transition in a hydrogen atom. And I'll just, note that we can only do this for hydrogen. We don't know the numbers for any other element. First of all, you can't find the wavelength directly. You can find the change in energy, though, for that electron as it drops from n equals 6 down to n equals 2. And that's going to be negative 2.18 times 10 to the minus 18 joules times 1 over nf squared. Remember, it's dropping down to n equals 2. So 2 is nf, and you square that. N initial would be where it started from, which is 6 in this case. So it's 1 over 6 squared. And of course, that's going to be the constant times 1/4 minus 1/36. You can do this on your calculator, and you find out that it's 0.2222. And when you multiply the constant by that, you get negative 4.84 times 10 to the minus 19 joules per photon. This is energy released, which is why the number comes out to be negative, because we measure energy changes from the standpoint of the atom itself. So if the atom is releasing energy, that would be negative because the atom is losing energy. In order to find the wavelength, we use E equals hc over lambda, and we rearrange it to find lambda is equal to hc over E. Okay, in this case, for the E, we drop the negative sign, because then if we left the negative sign in, we'd come out with a negative wavelength, and that's not possible. So we're just looking at the energy of the photon now. The negative number, was the change in energy of the atom. So the atom lost this much energy. That's why the number is negative. The energy that goes into this equation is the energy of the photon that was released from the atom. Due to conservation of energy, though, we know that the energy of the photon released from the atom must be the same as the amount by which the atom's energy decreased, only the energy of the photon is positive. So the energy was lost by the atom, but it was gained by the photon. And so this energy here is going to be the same number, but it's going to be positive. H is the constant, Planck's constant, 6.626 times 10 to the minus 34 joule seconds. C is the speed of light, 3 times 10 to the 8th meters per second. And then the energy, again, is positive 4.84 times 10 to the minus 19 joules. And when you work all that out, you get 4.11 times 10 to the minus 7 meters, or 411 nanometers. And that light is violet light. Okay, so as a summary, in hydrogen, transitions from n equals 6 or 5 or 3, or sorry, 6 or 5 or 4 or 3 to n equals 2 occur in the visible range. And in fact, hydrogen's atomic spectrum has 4 lines in the visible range, and they correspond to n equals 6 to 2, 5 to 2, 4 to 2, and 3 to 2. And we just saw what the wavelength is for 6 to 2. It's 411 nanometers. In hydrogen, if you go from 7 or above down to N equals 2, that's ultraviolet. And we can't see it with the naked eye. And transitions from basically N equals anything ending up in N equals 3 would be in the infrared. And anything that goes down all the way down to N equals 1 is, again, ultraviolet. So the transitions we see in hydrogen do not actually consist of the hydrogen atom going from an excited state back to the ground state. All of those transitions from 6, 5, 4, or 3 down to 2 represent hydrogen going from an excited state to a less excited state. N equals 1 is the ground state. But when hydrogen returns to the ground state, all of those lines are in the ultraviolet and we can't see them. Okay? Okay. For the next part, we go on to 7.6 and shapes of atomic orbitals. The shapes of the atomic orbitals are important to know for things like bonding, because bonding consists of sharing pairs of electrons between atoms. And if the orbitals control where the electrons are, they control where the bonds are. So the shapes of the orbitals have a lot to do with the shapes of molecules. And the shapes of molecules have a lot to do with things like polarity or reactivity of molecules, or even physical characteristics of molecules like melting point and boiling point. So actually, orbitals are really important. And so remember, it's the L quantum number that gives the shape of the orbital. The L quantum number is also associated with a letter designation. And it's basically the N quantum number that determines size and energy of the orbitals. And M sub L decides which particular example of that type of orbital you're talking about, or in other words, what is its orientation? Because that's how the various p-type or d-type orbitals differ from each other. Other orbitals of the same type, they differ in orientation. So if you know M sub L, you know which particular orbital of that type you're talking about, which is also its orientation. So for the S orbitals, these are the ones where L equals 0. S orbitals have the lowest energy of any orbital in a given shell. A 3D plot of the solution to the wave function. or in other words, psi squared, is the probability map. And the magnitude of psi squared is proportional to the probability of finding an electron in a given location. Okay, on the page 303, there's a diagram of an s orbital. I'm not going to bother showing it because it's actually very straightforward, pretty simple. The shape of an s orbital is spherical. And in terms of size, it will encompass about 90% of the total probability of finding an electron. You notice how, the edges of the sphere are kind of fuzzy, and that's because as you get further out, you get less and less chance of finding an electron. And very often we portray an s orbital as the probability map, with the fuzzy edges. But if we have to put a definite boundary on it, then we basically put a boundary around the area that represents a 90% probability of finding an electron. The simple diagram of an s orbital makes it appear as if the greatest probability of finding an electron is at the nucleus, but actually that's not the case. And if you do a radial distribution function, that is the total probability of finding an electron within a thin spherical shell at a distance r from the nucleus, you'll find that there is actually a node at the nucleus, a node just being an area where there's 0 or near 0 probability of finding an electron, and that the maximum probability for finding an electron for an s-type orbital is a little bit away from the nucleus. And that is exactly the kind of thing that you would expect. Okay, so that's basically what I just said. If you do a radial distribution function, you'll find out that actually, no, the probability of finding an electron is not greatest in the nucleus. It's actually the greatest just outside the nucleus. And if you do the similar function for s orbitals in the second or third shells, you'll find that their greatest possibility for finding electrons would be a little further out from the nucleus. 2 is a little further out from the nucleus than 1. 3 is a little further out than 2. And each s orbital holds a maximum of 2 electrons. Now for the p orbitals, things get a little more interesting. This is when L equals 1. These are the second lowest energy orbitals in any given shell that has them. And so that means that these are higher energy than S, but lower than any of the others. And p-type orbitals are only found starting in n equals 2. So there's no such thing as a p orbital in shell number 1. And it turns out that each shell that has p orbitals, that is n equals 2 on out, has 3 of them. And they differ in orientation. And the names that they're often given are px, py, and pz. To draw them, you can think of, or to see what they look like, they're kind of dumbbell shaped, and you can draw the 3 axes, x, y, and z. Px orbitals, if the nucleus is at the origin, would look something like this. They go along the x-axis. Py orbitals would go along the y-axis, like that. And a pz orbital would go along the z-axis, coming directly in and out of the page like that. Also, the, M sub L, the px, py, and pz correspond to the 3 values for M sub L. Because if L equals 1, the 3 possible values for M sub L would be -1, 0, and +1. So one of these orbitals would be -1 for M sub L, another would be 0, and the other one would be +1. And it doesn't really matter which is which, because all 3 of the p orbitals in a given shell have the same energy. And the technical term for multiple things that have the same energy is degenerate. So it's kind of interesting. No, they're not perverts. They just have the same energy. In science, degenerate means have the same energy. Okay. Each p-type orbital can hold a maximum of 2 electrons, which is 6 electrons total for the 3 of them collectively. And the main difference between the p orbitals in n equals 3 versus n equals 2 is just the p orbitals in n equals 3 have higher energy and they're bigger. But they're the same shape. And they hold the same number of electrons. Okay, so even though they're getting bigger, they can still accommodate the same number of electrons. All right, we come next to the d electrons. So the d orbitals. These are the ones where L equals 2. These are only found from the third shell on. So there are no 1d orbitals or 2d orbitals. They only start from 3 from the third shell. The d-type orbitals are fairly complicated in shape, and you don't really have to remember the shapes or their names. Just be aware that there are 5 of them. And so the 5 are actually dyz, dxy, dxz, dx squared minus y squared, and dz squared. And you can look on page 306 to see the shapes of them, if you like. They're kind of like a 4-leaf clover sort of shape. And the m sub L values, again, there are 5 m sub L values for d-type orbitals because there are 5 d-type orbitals. And each m sub L value would correspond to one of those names for a d-type orbital. But again, it also doesn't matter which number you assign to which name because once again, they are all the same energy. Or in other words, all degenerate. Within a given shell. Of course, 4d orbitals have higher energy than 3d orbitals, but the 3d orbitals all have the same energy as each other, and the 4d orbitals all have the same energy as each other. So as with the p orbitals, their main difference is in orientation, except for that one oddball dz squared. That has a different shape too. Each d orbital holds a maximum of 2 electrons. That's a kind of a universal thing for orbitals. No matter what type of orbital it is, any individual orbital can only hold 2 electrons. And that means that the d orbitals in a given shell can hold a maximum of 10 electrons. And moving on to the f orbitals. That's L equals 3. They are found from n equals 4 on up. And there are 7 f-type orbitals in each shell that has them. Their names are really weird, and the shapes are even weirder. You can see those on page 307 if you like. We don't really need to know the names or the shapes exactly, but we need to know that there are 7 of them in each shell that has them, and that the m sub L values are -3, 2, -2, -1, 0, 1, 2, 3. That's 7 numbers because there are 7 f-type orbitals. Each of these numbers would correspond to one of the names, but once again, they're all degenerate with each other. And with other types of orbitals, you can only hold a maximum of 2 electrons in any f-type orbital. And that means a total of 14 electrons in f orbitals for an entire shell. That's the maximum. There could be less. Okay, and the last thing in this chapter I wanted to mention is something the book actually doesn't. I'm sure it mentions it in the future, but I think it makes sense to mention it now. So I'm at least going to give you an introduction to the idea now. And that is the fourth quantum number. And that's known as m sub s. Or the spin quantum number. This quantum number refers not to an orbital, but to a specific electron within an orbital. So the first three quantum numbers are about narrowing down which individual orbital you're talking about. The fourth quantum number is about identifying which electron in that orbital you're talking about. Because remember, each orbital can hold 2 electrons. So you have to have a way of saying which of those 2 electrons are we talking about. And that's what the fourth quantum number, or the spin quantum number, is about. This is the only quantum number that is not a whole number value. The values for the spin quantum number would be either +1/2 or -1/2. And +1/2 is called spin up, and -1/2, take a guess, spin down. The electrons in the orbitals are not really spinning as such, but this is a name for a quality that allows electrons to be in a small space together at the same time without repelling each other. Because normally you'd expect negatively charged electrons to repel each other if you try to move them close together, like putting them in the same orbital. So the electrons have this quality that we call spin, and if they have opposite spin, then they don't repel each other. So they have to have opposite spins in order to be in the same orbital and avoid repulsion. So in a given orbital, one of the electrons will have a spin quantum number of +1/2, and the other one will have a spin quantum number -1/2. And now you can identify specifically which electron you're talking about. So the whole set of 4 quantum numbers will identify one particular electron in an atom. And it also means that each electron in a given atom will have a unique set of the 4 quantum numbers. You won't find any 2 electrons in an atom that have the same numbers for all 4 quantum numbers. At least one of them would have to be different. Okay, so that's at least one of them has to be different. And that is the end of chapter 7, and it's the 30-minute mark for this segment of the video too. So that was pretty well timed. So we'll be back next time with a new chapter. We're ahead of schedule, but again, I want to keep going and stay ahead of schedule because, well, at least now we're at the point where, according to the schedule, we only have to do 2 chapters next week instead of 3 like it originally said. So 2 chapters, we should be able to handle that. So we are a little ahead, but remember, the homework due dates are still based on the original schedules. So you'll be handing in homework on stuff that we did a while ago at this point, I guess. Anyway, I'll see you in the next lecture.